Okay, so the degree centrality is the number of neighbors of a vertex. So if you look at here, the degree of node 0 is 3. So the degree centrality of node 0 is 3. Node 1, it has 2 neighbors, so its degree centrality is 2, and so on. Now, how do you determine the degree centrality of a vertex? If you use an adjacency list representation, you can just count the size of the linked list, the number of neighbors of each vertex. Now, if you use an adjacency matrix based representation, you could compute the degree centrality like this, and we go through this approach because this is the approach we'll use to compute the other centrality metric called eigenvector centrality metric. So that's why I'm going to be showing this approach of computing the degree centrality using the adjacency matrix. Now you all know what an adjacency matrix from the previous module. So it's a square matrix, a symmetric matrix where the entries correspond to the vertices. So you have 8 vertices in this graph. So you have 0 through 7 or the node IDs. So that's the adjacency matrix. Now there is a 1 if there's an edge between the two vertices. So 0 and 1 have an edge between them. So there's a 1 for that cell entry here. Now it's a symmetric matrix. So 0 1 is same as having an edge between 1 0. So the entry for row 1 column 0 you also have a 1. So row 0 column 1 you have a 1. Row 1 column 0 you also have a 1. Similarly 2 3 have an edge, so it means row 2 column 3 you have a 1. Row 3 column 2 you also have a 1. Okay, so as I said in the previous module, it's an undirected edge, so that means we have an edge direction in both directions. Okay. So now what you have to do is you have to multiply the adjacency matrix by a unit vector or a column vector where all entries are ones. Okay, so now the rule for matrix multiplication is you have here an 8 row 8 column matrix, so it's 8 by 8 matrix, and this is an 8 row 1 column matrix. So in order to be able to multiply two matrices, the number of columns in the first matrix should be equal to the number of rows in the second matrix, and the dimension of the product matrix is the number of rows in the first matrix and the number of columns in the second matrix. So we have 8 rows in the first matrix and 1 column in the second matrix, so it's an 8 by 1 product matrix. So this cell corresponds to row 0 column 0, or the first column basically, right? So row 0 is this multiplied by column 0, which is this. So it is 0 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1 plus 0 times 1 plus 0 times 1 plus 0 times this one plus 0 times this one. So basically you multiply the pairwise and add them, and it's going to be 3 in this case, which is the degree of node 0. Now this cell corresponds to row 1 column 0, so that is row 1 multiplied by this column. So again pairwise multiplication, 1 times 1 plus 0 times 1 plus 1 times 1 plus 0 times 1 plus 0 times 1 and so on. So it's going to be 2. This entry is row 2 column 0, so row 2 column 0, so that's going to be 3. Okay, so now if you look at the time complexity of this process, you're doing right v vertices, right? So for each vertex, to compute its degree centrality, we do v multiplications, right? So we do like v columns multiplied by this one, and so totally there are v vertices, so it's v times v squared. So that's the time complexity of computing the degree centrality based on the adjacency matrix. Now remember, one main thing that we want to do with centrality matrix is to be able to find the most important vertices, so quantify the topological importance of the vertices in a network. Now the degree centrality is integer based, right? It's just the number of neighbors. So it is possible, like in this graph, several vertices have the largest number of neighbors. Like in this case, the largest degree is 3, and 4 vertices have this largest degree 0, 2, 3 and 5. So there, it is a possibility there could be ties among the vertices in order to find it, in order to rank them based on the degree of centrality. So that's the weakness of this centrality metric. Now the next centrality metric that we'll see, called eigenvector centrality metric, will try to alleviate this weakness as much as possible. Okay, so let me stop with this.